Good afternoon, everyone, and welcome to Bruker Daltonics demo lab in Billerica, Massachusetts. We had some technical issues. Apologies for that. The audio wasn't working. But today we will be showing you live how MALDI-TOF mass spec is used for the identification of adulterated cranberry foods and dietary supplements. So today I'm here with Chris, who is the CEO of Complete Phytochemical Solutions. And he will be taking over in just a few minutes, live from his lab in Cambridge, Madison as well, and show you the workflow in action. He'll have a couple of samples to go through with the presentation as well. So welcome. Just a few things. Make sure to adjust the different windows so you can see the presentation a lot clearer in a more readable way. Also, do not wait until the end to ask questions. You should have a window somewhere in one of the windows where you could type the questions as we go on, and we'll take the questions at the end of the presentation. So just a quick outline of how the next 45 minutes will go. First, we will briefly look at the MALDI-TOF process and how MALDI analysis works in general. And then I will give you a brief tour of our demo lab here in Billerica, show you some of the MALDI instruments that we use. And then after the tour, I will turn it over to Chris for a live demonstration on how to identify adulterated cranberry products with MALDI. And then after that, we'll conclude and answer some questions if we have any time left. So the MALDI-TOF process is a two-step. It's a two-step process. You have the MALDI, which is matrix-assisted laser desorption ionization. It's the ionization step, and then the next step, which is time-of-flight mass spectrometry, and that's for separating the ions, analyzing them before they get to the detector. And this is a quick video that shows the inside of the instrument, gives you a picture of basically what goes on behind the instrument, and hopefully will help you visualize what's going on as we show you the live demo. In the beginning, so in the first step, your samples are fixed and co-crystallized on the target, and they're bombarded by a laser in a vacuum. So the sample molecules vaporize in a vacuum while being ionized at the same time. And then after the ionization step, high voltage is applied on the target plate to accelerate any ionized particles or ionized molecules basically to the detector. So that's what you're seeing here in this video. And that basically is the first step, which is MALDI, the ionization step. And then the next step or the next phase is called time of flight mass spectrometry, in which the ions basically separate by mass, because you have a constant voltage across the whole plate. You have a constant tube of flight where the ions get to fly all the way to the detector. The only difference is the masses of the ions that have been formed, which also in turn gives them or results in different velocities or speeds. So in a linear mode, the ions will reach the detector in just a few nanoseconds after the ionization step. Higher mass molecules will arrive later than lighter ones. And flight time measurements for each ion detected are used directly to determine the mass of those ions. And then you turn that into a mass spectrum that you can read and interpret to know what sample you have. In a refractron mode, the ions, there's an added element. So those plates, the refractron plates are added and are used to divert the ions toward the secondary detector. And the combination of a longer flight tube or flight path and also the refraction plates that help focus the ions onto the secondary detector will result in higher resolving powers in refractory mode versus if you're using it in a linear mode. So hopefully that paints a picture and shows you what's going on behind inside of the instrument as we analyze some of the samples. So we have here at Bruker 3 levels of instrumentation, 3 levels of MALDI instrumentations, and of course, instrument choice will depend on the type of application that you need the instrument for. On the lower end is the Microflex LRF. It's a benchtop value, and this is a good option for simple MALDI experiments, for fast and easy QC of synthetic peptides, polymers, oligonucleotide, basically any kind of all types of samples. And plus, this doesn't take much space in your lab. It comes equipped with a 60 hertz nitrogen laser. It can be operated in both positive and negative ionization modes and has a mass range of up to 300 kilodalton, and can be operated in both linear and refraction mode as well. Next up in line, we have the AutoFlex Max, which is a vertical setup. And this is actually the instrument that we're going to be using for today's demo. It's the same one that you guys can see here next to me. And this is an all-around MALDI workhorse, basically, that can do almost anything and everything, all types of experiments that are possible with MALDI. And that includes top-down sequencing, that includes MSMS experiments, that includes MALDI imaging as well. And MSMS experiments are, or MSMS capabilities are very necessary for structural elucidation, as well as confident and specific compound identification as well. So MSMS experiments add a huge value to the instrument. So this one comes equipped with a 2000 hertz laser, Smart Beam 2 laser, and this is a solid state laser that lasts a very long time compared to a nitrogen laser. And it also has a mass range up to 500,000 Dalton, comes in different configurations. So you can have it in linear mode only, or linear and refraction mode, or TOF. And the nice thing about this is if you choose to go with the linear mode, for example, it's field upgradable. Basically, you can upgrade it over time to a linear and refraction or TOF MS experiments. Next up in line, we have the UltraFlex Stream. And I have this one actually sitting right behind me. The camera will cooperate. So it's a horizontal setup, and this is our gold standard for complex samples, including polymer analysis, copolymers, complex mixtures, or samples that may be into a complex matrix, and you have to pick it out, and you need high resolution to do that. This comes equipped with a 2000 hertz smart beam lasers, the same that you get in the AutoFlex Max, but in this case, you can actually do MSMS experiments at 1000 hertz repetition rates versus 200 hertz on the AutoFlex Max. It has a mass range up to 500,000 Dalton, and also TOF capabilities. And top of the chain comes the RapidFlex, which is also right in front of me. The RapidFlex is the best choice. It's the best that there is with higher specs, higher speeds, especially for imaging experiments. This one has the fastest laser in any MALDI instrument ever made. It could go up to 10 kilohertz repetition rates. It's equipped with a Smart Beam 3D laser, which is slightly different, more improved than the Smart Beam 2 laser that you get in the Autoflex and Ultraflex Stream. It has a high mass range up to 1 million Dalton, and also TOF capabilities as well. So now I will turn it over to Chris for a more hands-on and live demonstration of how you can use MALDI to identify adulterated cranberry foods and products. Just a few words of introduction about Chris. Chris is the CEO of Complete Phytochemical Solutions with over 25 years of experience in at the University of Wisconsin-Madison as a phytochemist, specializing in the development, validation, and harmonization of mass spectrometry methods for the authentication of dietary supplements, foods, beverages, all types of applications, basically. And he's also a member on several associations of official analytic chemists, AOAC. Most of you may be familiar with that association. He's on a lot of expert review panels and works closely with the American Botanical Association, ABC, the United States Pharmacopoeia, USP, to develop guidance documents and monograms as well. So without further ado, I will turn it over to Chris so that he can show us live how to identify adult rare cranberry products using MALDI. Chris, the floor is yours.
Thanks, Pierre. Can you see my presentation?
Yes, I can.
Okay. Well, let me get started and thank Pierre and Bruker for this opportunity. We're embarking on a collaborative effort here to promote the use of MALDI-TOF mass spectrometry to address evolving issues of adulteration in the natural product, botanical, food, beverage, and supplement space. So what we'd like to do today is focus in on an issue on regarding the adulteration of cranberry foods and dietary supplements, and just kind of use this as an example and a platform to demonstrate what a workflow looks like in a operating contract laboratory. I'm going to advance my slide here. See if I can do this across too many screens. There we go. Quick outline of the presentation today. I'll give a very brief introduction about Complete Phytochemical Solutions, who we are and what we do. We'll talk a little bit about the underlying principles of adulteration, exemplifying cranberry products. I'll introduce you to a class of compounds referred to as proanthocyanidins, or PACs for short. This is a bioactive class of oligomeric polyphenols found in cranberries that have unique characteristics that can be used to support the authenticity of the products. We'll perform a live demonstration of the MALDI workflow on our Autoflex instrument here in Cambridge. And then we'll look at the data, inspect the data, and interpret the data in relation to supporting authenticity. And then we'll have a brief conclusion. So let me give you a little bit of a background about Complete Phytochemical Solutions. We are a third-party analytic testing, contract research, and consulting service provider. We work across the continuum of the supply chain, or as we like to call it, the value chain. The supply chain is moving ingredients, parts and pieces from the start, the growers, the farmers of food crops, over to processors that may convert that fruit into a juice, a beverage, a dietary ingredient. We work with formulators who would blend various ingredients to be able to create unique products. And then we work with retailers, the individuals that position these products in the marketplace. This may be retail, grocery stores, it may be direct consumer, e-commerce. We like to refer to this as a value chain because in addition to the actual product that's moving, the physical product, there is also the supporting information and intellectual content that supports the manufacturing. So these would include certificates of analysis, specification sheets, different items that are used to certify authenticity at each stage in production. What we want to do is talk a little bit about the problem that's abundant in the natural product environment, and that's the problem of adulteration. So there's an economic motivation to adulterate high quality and efficacious food products, beverages, and dietary supplements with lower cost and potentially dangerous ingredients. So if you can fool the system and introduce a cheaper ingredient into a product, you can profit from that. And that's a dishonest practice and something that we're tasked with trying to address here as an analytic laboratory. This problem can occur in fruits and vegetables, dairy, meats, fish, oils, and this includes essential oils. So there's a need for rapid, high-resolution analytic methods that are fit for purpose to address the continually shifting issues of adulteration in complex botanical products. And I use the term fit for purpose, and what I mean by that is an analytic method or an instrument or combination thereof that is targeting a select compound or class of compounds that are the basis of the adulteration. In the case of cranberries, we're going to be focusing on our class of proanthocyanidins. So Complete Phytochemical Solutions is offering a solution to the issue of adulteration of botanicals. We have developed MALDI-TOF mass spectrometry methods to identify phytochemical profiles, or what we refer to as fingerprints, that are unique representations of a botanical, that be a fruit or a vegetable. And again, this is a wider applications into other food products such as dairies, meats, and oils as well. So cranberry adulteration is going to be the highlight of this presentation. We are going to talk about a class of compounds referred to as proanthocyanidins. And you're going to see a structure here that is a proanthocyanidin dimer. And we're going to talk about dimers and trimers and oligomers and polymers. But really fundamentally what we have is a repeating building block. Think about these as links in a chain. This repeating building block can be attached in series or in parallel to form these complex oligomeric compounds referred to as proanthocyanidins. So to start the discussion, we're going to focus in on a procyanidin dimer referred to as an A2 dimer. And what we're doing is we're looking at a compound in which there are two adjacent monomeric units connected through an A-type bond. And we'll talk a little bit more about bond, interflavin bond linkages. But in this introductory slide, suffice it to say that there's a unique class of compounds that's correlated with cranberry. And that same class of compounds, proanthocyanidins, can have a different type of bond referred to as a B-type bond. And this class of compounds may be present in fruits like apples. So these are the types of fingerprints that we're going to be looking at through our demonstration to be able to show a differentiation between cranberry and apple and potential adulterations and blends of those two products. So let's have a statement of what the real issue is. Back in 2017, this is only 3 or 4 years ago, it was brought to the attention by stakeholders in the industry that adulteration of cranberry products was occurring. And if we look at the total U.S. Consumer spend on dietary supplements, for example, we're looking at about a $9 to $10 billion a year industry. on supplements alone, and this isn't including foods and beverages. Cranberry is the 5th leading herbal supplement and has consistently been so. So the issue of adulteration of foods, beverages, and supplements in the cranberry stakeholders' viewpoint is a very critical issue to address. In 2017, the American Botanical Council published an adulteration bulletin calling attention to this issue in the marketplace. At the same time, U.S. Pharmacopoeia organized a cranberry roundtable in which they gathered stakeholder input for drafting monographs or guidance documents. And similarly, AOAC organized a cranberry working group that put out a call for a method that would be appropriate for the identification of A-type proanthocyanidins that are unique to cranberries. As a result of all of these efforts, Complete Phytochemical Solutions worked to develop, publish, and have accepted an official first action method to address the issue of adulteration of cranberry products. And that's the method we're going to be looking at today. What I want to do, and as Pierre said, we can do some adjustments to your to the way your platform is here, but I want to show you a few things in real time now, so you might want to expand the video and decrease the PowerPoint presentation. But what I have here is a stainless steel target. This is the target that will be introduced into the mass spectrometer. And I'll bring this up to the camera, and you can see that there's all little wells on here, and some of the wells have sample applied to them. And so what I want to do is introduce this now to the instrument, and while the instrument is loading the stainless steel target, we can give some other demonstrations of cranberry products in the marketplace. So this is as simple as placing the target on an extractable arm that's in the instrument. The arm is now going to retract into the instrument itself. There's going to be a vacuum that is pulled on the instrument, and soon we'll be able to analyze the little spots, the combination of the matrix and the analyte that were placed on the target. While the system is loading, I want to show a couple examples of cranberry products, some that may be familiar. Here's a cranberry juice. A lot of different varieties of these in the store. We have cranberry powder, and you can see a nice red color to the powder here. And this is an example of a whole milled cranberry powder. So if you take a cranberry, you homogenize it, you dry it. This is representative of that type of product that enters into the dietary supplement arena as an ingredient. And then I also have an example of some capsules. And in these capsules, you can place the raw powder either alone as cranberry standalone or in combination with other ingredients. And so very often we are asked to validate the authenticity of the cranberry at each and every one of these stages, at a juice concentrate stage, at a dietary fiber ingredient stage, in a filled capsule, in a final finished bottle product in the marketplace. So as you'll see from the PowerPoint presentation here, there's a number of different products that are represented, all the way from a juice, sweetened dried cranberries, whole fruits, dried ingredients, oils extracted from seed. Let's talk a little bit more about the chemistry of the proanthocyanidins, the class of compounds that we're paying particular attention to. As we mentioned, the A-type linkage is occurring between two adjacent monomeric catechin units. Proanthocyanidins is a general term for an oligomeric class of polyphenols, but there can be variation in the nature of that interflavan bond or linkage, A-type versus B-type. There can be different substitutions. In this case, you'll see a number of hydroxyl substitutions. These could be methoxylations. We could have different sugar moieties attached to the ring structures. So each plant really has its unique characteristics. And what's important to understand about cranberry proanthocyanidins is that they have biologic activity. And cranberries and cranberry products are promoted on the content of proanthocyanidins and their utility to address issues such as urinary tract health or gut health. So let me show you an example here of a bioactive aspect of the cranberry proanthocyanidins. This class of compounds with A-type linkages have the ability to cross-link or agglutinate pathogenic E. coli. And so this is a unique structure-function relationship that is being used to substantiate and market cranberry use in commerce. And so you can get an understanding of why it's important to authenticate this class of compounds. If this cranberry product were to be adulterated with a class of compounds in which there were no A-type interflavan linkages, this agglutination event would either not happen or would happen at a reduced level. So this is a good example of a fit-for-purpose approach in which the class of compounds that demonstrate the biologic activity are the directed focus of authentication. So what do we do here with MALDI-TOF mass spectrometry? We have the ability to detect the various ions generated from a compound. And what we're going to do today, as Pierre said, the MALDI can be run in both linear and reflectron mode. We're going to be performing our analysis in reflectron mode, and we're going to be performing it in a positive mode, meaning that the ions that are being detected are positively charged. And so what I want to do is first start by giving an example of an A-type bond. This is a procyanidin A2 dimer, and what you'll see is the expected mass spectral image or mass spectra that would be generated if this compound and this compound alone were analyzed. What we have here with this first peak is referred to as the monoisotopic peak, or the most abundant peak in this case. And then you have a number of other peaks that follow. These are representative of the isotope distribution, the naturally abundant isotope distribution found in nature. So as we know, carbon-12 exists, carbon-13, oxygen-16, oxygen-17. There are proportions of heavier compound elements that contribute to this isotope distribution. Similarly, if we are to look at a B-type proanthocyanidin dimer, we're going to see a similar isotope distribution. The difference between an A-type and a B-type is 2 atomic mass units. And that atomic mass unit difference is due to the loss of 2 hydrogen when a B-type bond is formed into an A-type bond. And so you can see the isotope distributions are similar, but your mass has shifted out 2 atomic mass units heavier. So our mass of interest is 599 for A-type and 601 for B-type. Now, if we were to be presented with a blend of these 2 compounds in equal proportions, we would come up with an isotope distribution that is reflective of the sum of these 2 isotope patterns. And so what we see is a unique pattern that is contributed by the 2 blended dimers. If we know the predicted ratios of isotope distribution, and we see this complex overlapping isotope pattern, we can deconvolute or disassemble these overlapping patterns and actually provide an estimate of the relative amount of these 2 compounds present. That is done through a series of matrix algebra calculations. And for those of you that are interested in learning more about matrix algebra, we have a publication by Dr. Feliciano back in 2012 that goes into great detail of how this calculation is performed. But suffice to say, the important aspects are we are understanding two targets, the AA2 and the B2 monoisotopes. We understand the relative abundance of those isotopes in nature. We have an observation of the intensity of the unknown sample, and applying matrix algebra, we can estimate with very high accuracy the relative composition or proportion of that blend. In this case, the known blend was 50-50, and our estimate was very close to that 50-50 ratio. We validated this application using 11 different ratios of A-type to B-type blends from 5% to 95%. And we were capable of estimating within 3% of our known blended ratios, demonstrating that this is a very powerful tool for not only identifying pure adulteration, but also partial adulteration of products in the marketplace. So what I would like to do now is switch away from the PowerPoint presentation and go into a real-time operation of the mass spectrometer to show you how we'll acquire data in the Flex Control software and then inspect that data in the Flex Analysis software. So I'm going to switch over now to the operation of the MALDI system. See if I can do this here. There we are. So I hope everybody can see now the Flex Analysis window. What we have in the upper right-hand corner here is a video feed from the inside of the mass spectrometer that is focusing on one of the wells on the stainless steel plates that we introduced earlier. I'm going to navigate to a location on the target that contains a Cranberry authentic proanthocyanidin reference material. And what I'm going to do now is acquire a data set by shooting this target with the laser at a laser power of 47%. So I'm just going to start the acquisition here. And this is the first time we've done this for a while, so it's going to take just a minute here to warm this up. There we go. And so you'll see as I collect this and hit the start button here, you'll see a little shot. That was the laser firing 200 times in that short time period. And what happened is we acquired this series of data. These peaks here are representative of Cranberry proanthocyanidins of varying polymer length. So this is the trimer, 3 links in the chain, tetramer, pentamer, hexamer, heptamer. And if we apply a label, it will give us the masses that are being acquired. So we can see in the case of the tetramer, the most predominant mass is 1175, reflective of a procyanidin that contains 1 A-type linkage. And we'll talk a little bit more about the inspection as we go on. Let me zoom back out here, and I'm going to remove the labels just again so we can see things more clearly. This is a good acquisition. We have good intensity of our samples of interest relative to the baseline noise. We have the ability to collect the 200 shots, and if we want to keep adding shots, we can keep summing this. We can collect another 200, and we can overlay then the summation to show how if we keep adding shots, these peaks of interest keep increasing above and beyond the baseline. So this is a quick demonstration of how rapidly we can introduce a sample into the instrument and acquire data that has a lot of value to support the authentication of Cranberry products. So I want to next transition into the Flex analysis window and show you the data set that I acquired earlier today. In Flex analysis, we're able to take the data that we just acquired on the instrument and inspect and include labels and determine signal to noise and absolute intensity of the peaks of interest. So what I want to show first is that this Cranberry reference material here, we can see that there is a polymer distribution. I'm going to blow this area up here. This is the trimer, and there's a mass difference of 288 units to the tetramer. That's the mass of an additional catechin unit. If we go from tetramer to pentamer, we increase the mass again by an additional catechin unit, 288 atomic mass units. If we zoom in on this tetramer, we will see that we have a complex series of overlapping isotope patterns. We have a procyanidin trimer in which all the interflavan linkages are B-type, a tetramer in which all the there's a single A-type linkage, again 2 atomic mass unit differences, the loss of 2 hydrogen and the formation of that bond, and a compound in which we have 2 A-type linkages, so the loss of an additional 2 hydrogen. This represents the unique fingerprint or profile of a Cranberry procyanidin tetramer. Now, I accumulated the data for another sample, and this one, for some reason, it's not letting me select. There we go. This is an apple procyanidin tetramer. And what we'll see is the most predominant mass at this degree of polymerization in the apple is reflective of an all B-type linkage. So if we overlay these two, you can see that there is a difference in this isotope distribution and the overlapping patterns. So this pattern in the blue is indicative of a apple proanthocyanidin, while red is unique to Cranberry. So if we were to have a product of an unknown origin, so we get a sample, there we go, that is an unknown that we receive at the lab, and we're asked to authenticate this product, we will collect the data and we will inspect this pattern and see how closely it resembles the pattern of the Cranberry. And what we're seeing is that in Cranberry, we would expect this isotope distribution to decrease across this continuum of peaks. In this particular product, this peak here at 1177 is higher than the preceding peak. I'm going to overlay again the Cranberry so that we can see the difference here. So Cranberry, the red, continues to go down, where the unknown sample, this particular peak, is exceeding our expectation of height. So we would suspect in this case that this product was adulterated with a other source of proanthocyanidins. And having built a robust library of potential adulterants, we can make a determination then that it's likely that this adulterant is apple proanthocyanidins, because this peak here in blue now is indicative of a apple all B-type interflavan linkage. So this is a way that we can acquire data quickly, analyze it quickly. I'm going to switch back now to the PowerPoint presentation again. Bring this up. And we can go through a little bit more explanation. Okay, thank you very much, Team Viewer. You can go goodbye. A little bit more about the explanation of what we just saw. Again, similar to what we did with the A-type dimer and the B-type dimer in the binary mixtures, we can take a more complex oligomeric distribution of cranberry proanthocyanidins and compare that to the distribution of apple proanthocyanidins. Again, each of these have a unique spectral fingerprint. And if these are blended at a known ratio, in this case a 50-50 ratio, the expected outcome would be a summation of these two complex overlapping isotope distributions. Once again, applying matrix algebra and deconvolution, we can estimate the relative contribution of A-type and B-type linkages at each degree of polymerization. And in the next slide here, we will see that graphically represented. So in the case of apples, the most predominant linkage is one that contains 0 A-types or all B-type. That's these purple bars. So greater than 90% of the apple proanthocyanidin linkages at each degree of polymerization from the trimer to the octamer contain all B-type linkage. That's a hallmark of apple. Where the cranberries, on the other hand, have a very low percentage of all B-type linkages, less than 10%, and a high contribution of one or more A-type linkages. So again, graphically, this is a representation of the relative abundance of A-type to B-type linkages at each degree of polymerization for a cranberry. So graphically, you can see there's a large and unique difference between these two products. Similar to what we did with the A2 and B2 dimer standards, we can do the same thing with cranberry proanthocyanidin and apple proanthocyanidins. We mixed these two products at varying ratios from 5% to 95% over 21 different ratios or blends. And we were able to look then at each degree of polymerization and determine that within 3% accuracy, we can estimate using the deconvolution application the amount of apple that was adulterated into a pure cranberry product. So again, a very robust and powerful high-resolution analytic tool that is fit for purpose. So as we conclude our presentation today, and before we open up to questions from the audience, we just want to summarize where we've been, and that is that we listened to stakeholder issues and concerns about the adulteration of botanical products. We developed a fit-for-purpose analytic tool and method utilizing MALDI-TOF mass spectrometry as a high-resolution, accurate mass instrument to address issues of adulteration. The MALDI provides fast data collection and automated processing. And this application, while today's demonstration was on cranberry, has a wide range of applications ranging across foods and beverages, dietary supplements. It includes milk and dairy. For instance, in those instances, we could look at proteins or peptides. If we were to analyze oils, we may be looking at phospholipids. And when we look at fish and meat, we would be looking at protein analysis. So this is a very robust platform. Complete Phytochemical Solutions will continue to work with the American Botanical Council, the U.S. Pharmacopoeia, and AOIC to listen to stakeholder concerns, identify and solve evolving stakeholder issues. And with that, I would like to close and thank a number of my collaborators, Dr. Jess Reed, the CSO at Complete Phytochemical Solutions, our team of analysts and researchers, and a couple postgraduate students, Dr. Feliciano and Dr. Escoval, who were instrumental in developing MALDI-TOF applications over the last 2 decades. So with that, I thank everybody for their attention, and I'll return this back to Pierre.
Yes, thank you, Chris, for that nice presentation and live demo. We've gotten quite a few samples, a few questions, and we'll try to answer as many as possible. So question number one, now this is for you, Chris. Can all samples be analyzed as received?
Okay, so yes, that's important. Some samples that are enriched in the class of compounds that we're interested in, for example, the proanthocyanidins, there are some very selective enriched extracts that may exceed 10, 20, 30% proanthocyanidin by weight. Those products are very well suited to be able to be reconstituted in an aqueous organic solvent, mixed with a matrix and deposited directly on the target. So very rapid analysis. Other products may be more dilute in the proanthocyanidin composition, and so simple front-end solid phase extraction preparations, such as using a C18 SEP pack or even pipette tips with a C18 resin embedded, can be used to clean those samples up, enrich the polyphenols away from other matrices like sugars or other excipients.
Thank you, Chris. Second question, on your first slide, the axis of the graph are cranberry percent predicted and percent measured. Do these refer to the concentration of packs measured in the sample?
On the, we think about the first slide, this was the predicted versus expected. Is that the question, Pierre?
I believe that's, yeah, I believe that's the slide in question.
Right. So what we did with both the reference standard, the A2 and the C and the B2 reference standard dimers, and the cranberry pack and the apple pack, is that those were blended at known concentrations. They were blinded. They were provided to the analyst. The analyst collected the data and then applied the deconvolution matrix algebra calculations to estimate the relative blend ratios. And those estimated blend ratios, or the known ratios, were then unblinded, and we were able to compare the observed or predicted ratio to the known or expected ratio. And we saw in both cases that we were within about 3% of estimating those blends when the relative ratios were unblinded. And I hope that helps answer the question.
Yeah. Yeah, thank you, Chris. And hopefully, if that doesn't, they can send us an email follow up.
Absolutely.
With more specifics. Besides cranberry, for what other dietary ingredients are you currently seeing adulteration issues?
In the marketplace right now, one of the biggest and fastest growing herbal supplements is elderberry. And with the COVID environment, there was a tremendous increase in the consumption of elderberries and elderberry products as individuals looked for alternative healthcare solutions through the natural product marketplace. Because of the growth and the importance of elderberry, it has become susceptible and a high target for adulteration. And so that is one of the botanicals that we're looking at very closely and trying to assist the marketplace and bringing solutions to support authentication of elderberry products and ingredients.
Right, right. Thank you, Chris. Next question. What do you use for a matrix for proanthocyanidins?
What we used today was a DHB, dihydroxybenzoic acid. In the past, we have also used transindyl acrylic acid. And so we've been successful with both of those matrices for the identification of proanthocyanidins.
Perfect, perfect. And then, yeah, I think we have a few minutes for a few more questions. In your presentation, you indicated that packs can have a degree of polymerization over 30, yet you only show data for degree of polymerization less than 8. Can you explain why?
Yes. So if everybody recalls from Pierre's early presentation, the MALDI is capable of detecting in both linear and reflectron mode. And the data that we looked at today and the application of the matrix algebra is uniquely suited for the reflectron, which gives us a lower mass range but higher resolution of the individual compounds. If we were to acquire the data on these same samples in the linear mode, we would increase our mass range and we would be able to detect polymers up to and in excess of 30 degrees of polymerization. There is not a theoretic limit to the size that we can detect. What I will say is that the larger the oligomer, the more complex the number of different iterations and variations at the degree of polymerization. So it becomes more difficult to resolve that from the baseline due to the complex nature of the polymer.
Thank you, Chris. Last question. We only have about a minute left. What are the classes of polyphenols could be used as markers for over-authentication?
Okay, so we have also looked at hydrolyzable tannins or elagitannins to support the authenticity of pomegranate ingredients, juices, and foods. Anthocyanins, the pigments of botanicals, are also well suited for MALDI. They are naturally charged species and fly as the mass themselves. They don't need to pick up another ion adduct. Flavonols and flavonol glycosides are also detectable by MALDI. So there's a lot of variation and targets that we can go after when we look at data for substantiation of authenticity.
Thank you, Chris. Thank you. Look, looks like this is the end to our live demonstration and presentation. If you sent a question to us, we've received it, and we will try to get back to you with some answers in the next few days. I want to thank Chris for the nice presentation and demo, and thank you all for attending. And I hope you guys have enjoyed the rest of your day.
Thank you, Pierre.